We will now start a new topic. This I will call Baire's theorem. And applications. So the four grand theorems of functional analysis. The first is the Banach, which we have already seen, and three others follow from what is called Baire's theorem. It's a theorem in topology. This actually Baire's theorem is not necessary, but then we will the proofs are quite nice and unified once you use Baire's theorem. The Banach theorem is all about convexity, and Baire's theorem is all about completeness. So we will study Banach spaces this time only, and therefore we will need a lot of completeness. So let us first recall what is Baire's theorem. So we have XD complete metric space. And you have Vn, n equals 1 to infinity, collection of open and dense sets. Then intersection n equals 1 to infinity Vn is also dense. So in a complete metric space, you have a countable intersection of open dense sets. The intersection is also dense. Countable intersection of open sets is not an open set in general. We know that in arbitrary only finite intersections are there. But these are what are called G delta sets. A G delta set is a countable intersection of open sets. So if you have a countable collection of open dense sets, the intersection is a dense G delta, if you want to use the jargon. Okay, so proof. So let W not empty be open in X. So we need to show W intersection n equals 1 to infinity Vn is non-empty. So then every open set will meet the intersection, and therefore the intersection is automatically dense. So first V1 is dense, therefore W intersection V1 is not empty. Also W intersection V1 is open. So if x0 belongs to, so let us say x1, belongs to W intersection V1, we can find a ball such that the ball center x1 and radius say r1 is contained in W intersection V1. In fact, we can take a smaller r if necessary, and therefore we will even assume that the ball closure of the ball radius center x1 radius r1 is in W intersection V1. So there exists. So now we are going to make an induction hypothesis. So assume, and we can also choose r1, which is of course positive, to be less than 1. We have found xi, I equals 1 to n minus 1, ri, I equals 1 to n minus 1, such that B of xi ri is contained in Vi, in fact the closure is contained in Vi intersection B of xi minus 1 ri minus 1 for I greater than equal to 1. Okay, so we have done that for I equals 1, and therefore we are okay. Okay, then we are going to find the next one, and also second condition is 0 less than Ri less than 1 by I. So these are the two conditions in the induction hypothesis which you are going to do. Okay, so now we take Vn is dense, therefore, and B of xn minus 1 radius Rn minus 1 is also open, and therefore there exists an xn in Vn intersection B of xn minus 1 Rn minus 1. Again this set Vn intersection B xn minus 1 Rn minus 1 is open, and therefore it will contain a ball which is centered at xn and of a positive radius. We shrink the radius if necessary, and therefore there exists Rn less than 1 by n such that B of xn Rn closure is contained in Vn intersection B xn minus 1 Rn minus 1. Okay. So what have we constructed? We have constructed a sequence xi, and this B of xi Ri closure is contained in the previous ball. So you have a family of decreasing balls, and therefore if you take any I bigger than n, j bigger than n, then you have xi xj will belong to B of xn Rn, and therefore distance of xi xj will be less than or equal to the diameter, which is 2 times Rn, and that is 2 by n, and therefore xi is quotient. And x is complete, so we have used all our hypotheses. This implies xi will converge to some x belonging to x. Okay, so we have found a candidate, and now you take for any I bigger than n, you have xi belongs to B of xn Rn, and therefore you have all the xi's are there, xi's converge to x, so x belongs to B of xn Rn closure, and therefore which is contained in Vn. So x belongs to Vn, so this implies that x belongs to intersection n Vn. Also x belongs to B of x1 R1 closure, and this implies that x belongs to W, and therefore we have found a common element in W and the intersection, and that completes the proof. Okay, so some remarks. So the significance of this result is not really the denseness of intersection B. So the significance of this result is that intersection n Vn is non-empty. That is how it's often used. The density is not of that much of a consequence. Okay, and also you can state this theorem in a slightly different way. So if you have an open dense set, then Vn complement, so Vn open dense implies Vn complement is closed and nowhere dense. And therefore the theorem can also be stated, so Baire's theorem can also be stated as follows: a complete metric space is not the countable union of closed nowhere dense sets so in fact it's you don't need closed, because if you just say nowhere dense sets, it's even smaller, and therefore it cannot be the countable. Now a set which is called which is the countable union of nowhere dense sets is usually called a first category, and everything which is not first category is called second category. And Baire's theorem says that complete metric space is therefore a of second category, and that's why it is called sometimes the Baire category theorem. But that's just category, has nothing to do really with what we're going to do, and therefore we'll just call it Baire's theorem and be done with it. Now, corollary: in a complete metric space, the countable intersection of dense G delta sets is a dense G delta set. Okay, now what does this mean? So G delta set is the countable intersection of open sets. So we have Wn dense G delta, means Wn is the intersection over M equals 1 to infinity Vnm. Okay, so the countable Vnm, so Vn open, and since Wn is dense, these are also dense. So if you take intersection Wn, so this will be intersection over N, intersection over M, Vnm, and that's again a countable intersection of open dense sets, and therefore it is also dense. And since it's a countable intersection of open sets, it is also a G delta set. Therefore, a complete metric space countable intersection of dense G deltas is also dense G delta set. Now, corollary 2, in a complete metric space without isolated points, that means singletons are not open sets. Okay, singleton is not isolated. You can't put a ball where nothing else is there. So singletons, that will become automatically open. So singletons open is ruled out. So this is a normal, it's a natural kind of space which we come across all the time. So in a complete metric space without isolated points, countable dense set is not a G delta set. So when I say in such a metric space without isolated points, when I say dense G delta, that means the set is automatically uncountable. So that is how this corollary is going to be used. Namely, if you have a complete metric space without isolated points and you have a dense G delta, then it is automatically uncountable. Okay, so there are lots of points where these things, where something happens. So proof. So let us take E to be xk, k equals 1 to infinity, a countable dense set. So if it is a G delta, if E is a G delta, then E can be written as intersection Vn, n equals 1 to infinity, Vn open. And then obviously, so Vn is also dense because it's bigger than a dense set. So now if you took Wn equals Vn minus union k equals 1 to n xk. So I am removing k points. And this is where the non-isolation comes in. When you don't have isolated points, Wn is also dense because singletons are not open and I am only removing singletons. So every open set Vn is already dense. So this is also dense and of course it is open. And now if you take intersection Wn, I will remove slowly all the x's, namely E, and E is the intersection of Vn, and therefore this has to be empty, which contradiction to Baire's theorem, and therefore this is not possible. Okay, so we have that if you do not have isolated points, then you only have it has to be dense G delta will automatically be a uncountable set. So the Baire's category theorem has several applications, and in this section we will see its application to Banach spaces. Okay, so but apart from that there are others. For instance, one of the applications is that continuous functions which are nowhere differentiable. Now if you want to give an example of that, it's quite difficult. Weierstrass has constructed one, and you might have seen it in the analysis course, but Baire category theorem can be used to prove that the number of such functions is really very large. Okay, it's an uncountable set, and the chances are that if you close your eyes and pick at random a function from C01, it is going to be nowhere differentiable. Okay, and this is the basis of Brownian motion in probability theory and so on. Okay, anyway, so now we will do some applications in functional analysis. So the first application of Baire category theorem is the principle of uniform boundedness. Okay, so theorem, this is called the Banach-Steinhaus theorem. So V Banach and W non-linear space. So I am not assuming W is complete. Okay, I arbitrary indexing set. So this could be finite, countable, uncountable, whatever. Okay, and let Ti belong to LVW, bounded linear operator from V to W for I in I. Then so there are two alternatives: either there exists an M positive such that norm Ti is less than or equal to M for all I in I. So the Ti's are uniformly bounded. So you see the title which is coming up here. Or sup norm Ti of x I in I equals plus infinity for all x belonging to a dense G delta set. So you see the sup of norm Tx infinity will blow up for a large number of points. We just saw that dense G deltas in a usual space without isolated points is in fact uncountable, and therefore this. Okay, so proof. So you define for x in V phi x, so this is definition, namely sup norm Ti of x I in I, and you set Vn equals set of all x in V such that phi x is bigger than. Now norm is a continuous function, Ti's are all continuous functions, and therefore one can easily check, so easy to check Vn is open for all. So now one of two things only can happen, namely all the Vn's may be dense or there may be a Vn which is not dense. Okay, so first assume there exists an n such that Vn is not dense. Then there exists x naught in B and an R positive such that B x naught R intersection B is empty. It won't intersect. Okay. So for all therefore for all norm x strictly less than R, what do you know about, we have that phi of x plus x naught. So this belongs to the ball Bx naught R, and that is not in n, which means the supremum is not bigger than n, so supremum has to be less than or equal to n. So implies that norm Ti of x plus x naught is less than or equal to n for all n. So you now choose norm x less than or equal to r by 2, our usual trick, so that it is always strictly less than r, and then for all I in I, what do you have? Norm Ti of x is less than or equal to, by the triangle inequality, Ti of x plus x naught plus norm Ti of x naught, and each one is less than or equal to n, and therefore this is less than or equal to 2n, and this implies that for all I, so this is supremum is less than or equal to n if norm x is less than r by 2, so this means that norm Ti is less than or equal to 4n by r, and this you can call as the m. So this is the first alternative. So the second alternative is all Vn are dense. Therefore intersection Vn is a dense G delta, and if x belongs to intersection Vn, what does it mean? Phi x is bigger than n for all n, implies phi x equals plus infinity, and that is precisely what the theorem is saying. Okay, so this is called the Banach-Steinhaus theorem, and now we will state a corollary which is the usual form in most books. Okay, so V Banach and W norm linear space, Ti belong to LVW, I in some indexing set I. Okay, assume sup norm Tix I in I is strictly less than plus infinity for all n. For all x in V. Then there exists an m positive such that norm Ti is less than or equal to m for all I. So we have simply excluded the second possibility, and therefore this is just the first possibility in the previous theorem, and therefore you have pointwise bounded implies uniformly bounded. So that is why this is called the uniform boundedness principle. Okay, another simple corollary. So V Banach and W non-linear space, and Tn sequence in LVW such that Tx equals limit n tending to infinity Tnx exists for all x in x in V. Then T belongs to LVW and norm T is less than or equal to lim inf of norm T. So proof. So Tnx convergent implies bounded. Therefore, norm Tn has to be less than or equal to some m, as we know from the previous corollary. T is clearly linear. Therefore, norm Tnx is less than or equal to norm T times norm x, and that is less than or equal to m times norm x. And therefore, if you pass to the limit, you get norm Tx is less than or equal to m times norm x, and this implies that T belongs to LVW. So pointwise limit of bounded linear operators is also a bounded linear operator if V is Banach. Okay. And now if you look at this part of the equation, so from this, if you take for all norm x less than or equal to 1, you have norm Tnx is less than or equal to norm Tn, okay, and therefore if you took limit on each side, so you get norm Tnx is less than or equal to lim inf norm Tn, and therefore you have norm Tx, because I am taking the limit. This side I take lim inf on both sides, so here you have a limit, there you have a lim inf, and therefore norm T is less than or equal to lim inf norm T. Okay, next corollary is again a very nice corollary. Okay, so V Banach and B contained in V some set. Assume that for every f in V star, f of B equals set of all fx, x is in B, is a bounded set in R or C, whichever is a scalar field. So this set of all numbers, and therefore it is bounded. Then B is bounded in B. So proof, you look at V to V double star, the mapping J. So set of all fx x in B is bounded. So FB is nothing but set of all jx of f x in B. So all the jx's, these are all bounded. So by the Hahn-Banach theorem, norm jx is less than or equal to C for all x in B. But J is an isometry and this is just norm x. So norm x is less than or equal to C for all x in B, and therefore it is bounded. Now this is, what do we do in finite dimensions? Suppose I want to see if a set is bounded. I will project it to this, to the x-axis, project it to the y-axis, and if this image is bounded, then I say X is bounded, because it will be contained in the box which is the product of these two things, and that is exactly what we are doing here. Now the projections to the coordinate axis are nothing but a basis to the dual space, and therefore if it is bounded for the basis, it will be bounded for all linear combinations. So and in infinite dimensional version is this corollary. Later on, when we study weak topology, this corollary will be can be restated in the following mode: weakly bounded implies bounded. Weakly bounded means the image under any continuous linear functional is bounded, and then that means that the set is norm bounded. So this is again a nice corollary. Okay, so we will now look at a very nice application of the uniform bounded principle to analysis. Okay.